Okay, so one thing you might be thinking is, well, if something expands, when I heat it up, put a flame under it, does it get less dense? Well, let's find out. So we're going to figure out the density of nickel. We're not going to do it at room temperature. We're going to do it at 500 degrees Celsius. And so it's room temperature 1. Let's see here, which will be roughly 23 degrees Celsius, is equal to 8.902 grams per centimeter cubed. So what is this guy going to be here? Is it going to change? Is it going to be the same? Is it going to be bigger? Is it going to be smaller? I'm just going to tell you that it's going to get bigger. Or sorry, the density is going to get smaller. Something else it tells us is that our volume coefficient for thermal expansion, you're just going to assume that this is 3 times the linear coefficient of thermal expansion, which we can look up in the tables. For nickel, that's 13.3 times 10 to negative 6. Okay. So, with that being said, let's get to it. So let's figure out how much our volume has changed from room temperature to 500 degrees Celsius. To do this, I can do it in various ways. I don't have to give a number. I'm going to just say that my volume initial is equal to 1 centimeter cubed. Why? Because ones are really, really easy to make things work. And so I'm just going to use that. I shouldn't use V initial. Let's try to use the same thing that your textbook uses, V naught. Okay. And so with that, this is not necessarily like strain in this regard. I would use a different symbol, but I'm not going to worry about that too much. When it comes to this coefficient for thermal expansion, just like the linear one was equal to delta over length naught, the volume one is going to be equal to my volume over my initial volume. So very similar equation. Very similar equation here. Okay, so we're trying to figure out what this volume is at the end. So let's go ahead and solve for that. Let's see here. So V over V naught is going to be equal to my volume coefficient of thermal expansion, which I don't actually know, so it'll be 3 times the linear coefficient of thermal expansion times the change in temperature, which will be equal to 3 times 13.3 times 10 to negative 6 per degree Celsius, then finally times my change in temperature. As a note, your textbook is saying that 20 degrees is room temperature. I'm going to go with that because that's a nicer number than 23. There we go. So when I plug this in my calculator, what do I get? I get a value of 0.019152. There we go. That looks good. Oh, ha! This is change in volume right here. I knew I was missing something. Change in volume for both of those. Forgot a delta, my bad. Okay, so this is my change in volume, and this would be in what my units were earlier. I'm just going to say centimeters cubed. Perfection. So then what's my final volume? Well, my final volume is going to be equal to my initial volume plus this change in volume. And so my final volume will be equal to 1.01915 centimeters cubed. The reason I chose a centimeter cubed for my initial volume is because what's in the bottom of our units for density, it's a centimeter cubed. So I can just easily tell how much mass will be there, and I can easily compare these values. So With that, I would find that my final density, I'll put a little f here so we know it's final, is going to be equal to 8.902 grams, because that's how much mass I would have had in 1 centimeter cubed, all over my new volume, which is 1.01915 centimeters cubed. And that's equal to 8.735 grams per centimeter cubed. So, did it go down? The answer is yes, it went down. Why did it go down? It went down because we're heating it up. It's expanding, and therefore the same amount of mass is being spread out over a larger area. Now, I want to take this a little bit further here. So, when I heat something up, another thing that's going to happen with metals is that we're going to have vacancies begin to be formed. So I might have a metal that looks like this, but as I heat it up, I'm going to start having gaps because the atoms are going to start moving. They don't just disappear, they move somewhere else. And as you can see there, that means that my volume is going to be even larger, even though my mass is staying the same. So I'm going to actually have a lower density than this. So let's go ahead and do that. Now, we will need to know a little bit more information. We're going to be pulling that the energy of vacancy formation is going to be 0.9 electrovolts per atom. So that's something we'll need to know. So energy of vacancy formation is 0.9 electrovolts per atom. There we go. Okay. So now let's figure out how many vacancies we have inside of this little block of nickel that we're dealing with. I believe this is a nickel from our previous part. Let's see. Yes, nickel. We can do this. We can do this. Let's get to it. Okay, first off, how many nickel atoms do I have? Well, so the amount of nickel atoms I have is going to be equal to Avogadro's number times the density of nickel all over the atomic mass of nickel. So we have a lot of information. As a note, we're using the density that's already been expanded by changing temperature. So in this case, it'll be 8.735. The Na, that's Avogadro's number, so 6.022 times 10 to the 23rd. Our density, which is 8.735 grams per centimeter cubed. And then finally, the atomic weight of nickel, which is 58.69 grams per mole. So what this gives me then, after doing all that, is actually the number of atoms I have per cubic centimeter. So let's plug that in our calculators. And that comes out to be 8.962, actually making that 3, 8.963 times 10 to the 22nd atoms per centimeter cubed. Okay, fantastic. Now, how many vacancies do I have? How many of these are actually vacant because the atoms have moved somewhere else? Well, my number of vacancies is equal to my number of atoms times the exponential of the energy for vacancy formation over Boltzmann's constant times temperature. So let's plug that into what we get. So that's 8.963 times 10 to the 22nd times the exponential of, let's see here, make sure I do this right. Yes, negative 0.9 over 8.62 times 10 to the negative fifth. That's in electrovolts. So this is also electrovolts. And then finally times the temperature, which is 500 degrees Celsius. But we don't do things in relative units. We have to change that. So this would be 773 Kelvin. Okay, Kelvins cancel, electrovolts cancel. I'm left with atom right here, left with atoms. Okay, so when we plug in our calculator, we'll get a smaller number, but still appreciable for the number of vacancies. So I get my number of vacancies is going to be equal to 1.220 times 10 to the 17th. Okay, so that's vacancies per centimeter cubed. Fantastic. So we are getting closer and closer to having our answer for the density here. But we got some more steps to go. Now, having done this, there is a longer pathway to finding the change in density based on the vacancies. You have to look into the unit cell, but I'll give you a little shortcut that works pretty well for me. So this ratio, the vacancies to the number of lattice sites, well, this is more or less telling you how much your density is changing. So if I want to find out how much my density is changing, then I just multiply my original density by this. Is it perfect? No, but it's a very similar form to what we've seen. And it's only off by like 1/10,000th of a percent, so I think it's good enough for most things. So let's plug that in there and see what we see. First off, what's my density? There it is, okay. So this would be equal to 1.220 times 10 to the 17th over the number of lattice sites, which is 8.963 times 10 to the 22nd, finally multiplied by 8.735. As note, this is going to be negative. Why? Because it's going to be getting smaller as we go. So let's plug that into our calculators. So 1.220 times 10 to the 17th divided by 8.963 times 10 to the 22nd, multiplied by 8.735, and this is hardly changing at all. So my density change is only 1.188 times 10 to the negative 5th. So I wouldn't even be able to see this. Like that's where the change is coming. Actually, I was supposed to be subtracting here, but I would actually just completely say it's a wash. At 500 degrees Celsius, the change due to vacancies is negligible. So my density is really just constant. Cool. So thanks for listening. As a note, if I increase my temperature change like to, I don't know, 1500 Kelvin or something, or 1500 degrees Celsius, I would definitely begin to see a change in the density at that point. 500 degrees Celsius is just too small for us, but the process will be the same. So that's it for this time. Have a good one, everybody. I'll see y'all later. Bye-bye.